Alright, so this is our 4305 team. My name is Matt, and
I'm Billy.
Alright, so the first part of the code, we go over the general system details, which include the center frequency, the sampling frequency, the sampling period, and the different frame size and num frames, and all the different constants that we will use throughout the lab. And then first, how we split it up was we split up the different bits that you're going to receive into the packet into different, sorry, we scrolled down, into different names. So first, we had the preamble bits, and we defined that to be what we're going to be getting when we actually do the simulation. Then we have the temperature bits, which we already defined to be 90 degrees according to this bit pattern. Then we did the pressure bits, and the flag bits, and the ID bits as well. And then we didn't do random bits because we wanted to see that we were getting the correct data at the output. And we could easily generate random bits, but I think it's more useful for the simulation to use all these bits. And then we also had the CRC as well. And then what we did was we concatenated horizontally all those bits together, but we excluded the preamble.
Okay. And then once we encoded the bits in Manchester coding, we can plot the unencoded data versus the encoded data. And if you see here, the blue represents the Manchester encoded data, and the blue represents the unencoded data, and the red represents the Manchester encoded data. Next, we are going to modulate it. For TPMS systems, they can have either ASK modulation or FSK modulation. In this simulation, we're using FSK modulation, and so we modulate the encoded data using FSK. And then we can plot the unmodulated data versus the modulated data. And you can see that the red signal is the modulated data, and the blue represents the Manchester encoded data bits.
Alright, so the next part of this is sending the signal through the transmitter filter. And for this, we use the Arcos design with a square root, similar to the last lab. And then what we did was we added noise to this signal using the com.awgn channel. This creates the white Gaussian noise, and with those different constants defined as well. The next thing we did was we plotted the unnoisy and noisy data. And as you can see, like, here we go, we're going to run the section. So clearly you can see that the red signal here is going to be our noisy data, and it is very noisy. And our blue signal, it's kind of hard to see, but it is the unnoisy signal. And the next part, we added a phase offset, and to do this, all you needed to do was use the communications toolbox for phase frequency offset, and then we set the phase offset to 90 degrees. And when you run the section, as you can see by the constellation diagrams, to the left you have the 90-degree phase shift signal, and to the right you have the unphased signal.
Next, we're going to add the timing offset. This is similar to what we did in the first lab, and we're going to add the offset to the signal using the variable fractional delay, and then we can plot the timing offset. So this shows the before signal and the after signal being with the timing offset implemented. And then we send the signal through the receive filter and we downsample it. And from there we go on to the PLL.
Yep, so here we set up the PLL. We have the input signal. It's put into the PLL. And then this is from the last lab that you guys kind of gave to us. We just run through the whole thing. All the constellation diagrams are set up. And then once you get to the last final part, this is the following is going to be what you see. Just one moment. Yep, right over here. Yeah, so I've experienced some technical difficulties. I don't know, I'm not exactly sure why, so sorry. Here we go. Sorry for that. Our part did not run for some reason, but here it comes. Again, sorry about that. Here it is. So this is our constellation diagram for the PLL. As you can see, the signal total somewhat locks. There you go. This is what you get. This is similar to the constellation diagram you saw at the input.
Next, we can decode the data. Then we broke it up, the decoded data, into its separate parts, so we can recover the preamble, the ID, the temperature, the pressure, the flag, and the CRC. For example, if we decoded the temperature bits, and then we converted the binary to decimal, and if you test that out, you can see that we get a temperature of 90 degrees. And the functions that we used for the Manchester encoding and decoding come from one of the MQP projects. And the function for converting hex to binary we also used from the MQP project.
Alright, thank you.